So let me tell you about, so the paper has several results, and the kind of like, some of the results are in the weeds. So, and it's a broad audience. So my goal is not to like give you a lot of proofs or things like that, but to expose to you what is this notion of non-uniform fault models, and what are the kind of motivations for it, and what are some of the high-level ideas, and a lot of open problems for the people interested in approximation algorithms or network design or graph algorithms in general. So that's my main goal. Yeah. So this is the talk outline. I'll tell you a little bit about network design and what is the motivation for this non-uniform notion. And then there are two models we considered, and I'll tell you a little bit about the techniques that underlie these two results. Yeah. And then a connection between them. Okay, so let me start with some background on network design, right? And this is a broad area, and so the overall setup, even though the applications come from many areas, is that I start with some underlying network, right? Like G is some underlying network, and I want to select a sub-network of that satisfies some constraints that I want, right? And many interesting problems that we study from basic undergrad algorithms are special cases of this model, right? For example, if you want the ST shortest path, then I just want to connect SNT. What is the cheapest way to do it, right? That's easy to see. If you want to compute the minimum spanning tree in a graph, that's also what is the cheapest subgraph of the original graph that is connected, right? So in this talk, we'll be interested mainly in this class of problems where I want to connect things, and I want a cheap subgraph of the original graph. Yeah. So when I was working at Lucent Bell, for example, the motivation would be like telecommunication networks. They are doing optical networks. So there are many different scenarios in which this kind of coincides. And yeah, so I forgot this thing. And in particular, this talk will be interested in higher connectivity requirements and fault tolerance as the motivation. So what is higher connectivity? So we say that if I give you a graph and give towards the SNT are k edge connected. If they are k edges, one pass from S to T, right? And why are we interested in that? If SNT are k edge connected, even if you remove k minus 1 edges, any k minus 1 edges, then SNT is still connected. So they're fault tolerant, right? Of course, you can also consider vertex connectivity, but in this talk, I won't talk about it. Yeah, it's a little more involved. Okay. And so, there are many interesting problems where we want to find a sub-network which is cheap of a given network that it satisfies some higher connectivity. So this one of the simplest thing is like if I give you an SNT and say I want to find cheapest k edge disjoint paths, how would we solve it? What is the algorithm? Interactive, so you have to reflect, not passive, right? So you can solve it using min cost flow, right? Min cost flow is what you use to solve it exactly in problem, right? Okay, but let's look at, say I want a graph so that subgraph such that it is k edge connected. That means I want to make sure that even if I remove k minus 1 edges, the whole graph is still connected. Okay, that's called k edge connected spanning subgraph problem. So it's a generalization of MST, right? MST is just one connectivity. Now, so unlike say SNT, which where we can go up to any k by min flow, algorithms to kind of handle this kind of difficult. Yeah. Okay. And then there's a very, very general problem called survivable network design problem. Okay. And let me define it for you. And it's a classical problem in approximation algorithms. And it's among other things motivated by fault tolerant network design. So it's very general in the following sense, right? What is the input to this problem? I start with a graph and edge cost as before. And now for every pair of vertices SNT, I tell you I want this much edge connectivity, right? So I want 5 for this pair, 2 for that pair. So every pair I can tell you a different edge connectivity. And what is your goal? You want to design a sub-network such that that satisfies this connectivity requirement. Yeah, so fairly general problem. So here is an example. for example, and I give you this graph, and I'm only interested in saying, oh, S1 T1 you should have 2 edge connectivity, S2 T2 you want 2, and S3 T2 you want 1, right? You can specify for all pairs, but I just want to show 3 pairs. And a feasible solution could be this set of dotted edges, right? You have to check that it's all true, but let's not worry. Yeah. Okay, so you can see that S1 yeah. Yeah, it's a generalization. It's much stronger generalization, right? It's a very broad and it's kind of 2, 3, whatever I want. Amazingly, you can get a 2 approximation for this very, very general problem, right? And this is one of the fundamental results in approximation algorithms due to Jain, not real Jain, but Kamal Jain many years ago. And it's based on this very, very powerful technique called iterated rounding, right? And it's like a cornerstone technique since then. It's something that important. And oh yeah, scheme submodel, something. There's a lot of connection submodel. It's a beautiful result. And but I also mentioned that before this powerful result, there were previous results, which also are based on and we kind of rely on those kind of slightly weaker results. This primal dole algorithms based on augmentation. That I'm just mentioning this because it come up again. This is a very powerful result, but it requires some structure which may not have. Okay, so now I mean, what the motivation for this talk of our work was like what we call non-uniform model, right? So what is non-uniform? So when we ask for k-edge connectivity, we are asking this requirement that any k-1 edges can fail, right? And so we want this strong requirement. But some many scenarios, maybe there are correlation between edges, right? These 2 edges are likely to fail together, while those 2 will not fail together, yeah, for some reason, right? And or like some edges are more likely to fail than other edges, right? So people would like to model this non-uniformity and correlations in what edges can fail, right? And now, how do you model that, right? And so the practical motivation is like, how do you take this into account? And theoretically, like one can define whatever one wants, but then sometimes they become too hard, right? Is there some tractability? Also, from a technical point of view, we want to develop new ideas when they push us, right? Right? Necessity is the mother of invention, right? So if you don't have a new problem, we won't develop always new techniques. Sometimes you have to play this game from a practical or theoretical point, right? So okay. So in this talk, I'll discuss 2 models that we study, right? And there are connections between these 2, and we'll explore this. So, and these models were not introduced by us; we were led to them by some previous work, and so they're both kind of suggested by Adjiashvili, who has been interested in this non-uniform model for a while. And there's another 3rd model which I won't talk about because it's like there's only so much time, and you can look at the paper. Okay. So what is this first model? This first model is a slight twist on the standard model, right? So I have a graph, right? But now I have 2 classes of edges, right? What are called safe edges and unsafe edges. Okay. So the safe edges, think of them as green edges, and unsafe edges, red edges. So the model here is that only unsafe edges can fail. Okay, there are some very good edges, maybe you have to pay more to buy them. But then there are other edges that they are not, they're a little flaky. So we categorize the edges into safe and unsafe, right? And only unsafe edges can fail, right? And so now again, at high level, the problem is the same. You want to design a network robust to failing of unsafe edges, right? So let's look at the sort of maybe the same, yeah.
Weighted?
No, the edges have weights.
Like is there a certain pre-augmentation problem and this problem? Let's say.
Yeah, there is that. Let me give an example, and I'll right. Take some time to understand this, so I'll give an example. Yeah. Okay. So let's one can define a very general model, but this initial paper studied the following very simple setting, right? So I have a graph as before, and you want an E is again partition with safe unsafe edges. and only one unsafe edge can fail, right? Say, not can fail. I mean, you want to be robust to one unsafe edge, right? So you want to find a cheapest subgraph so that even if one of those unsafe edges in the subgraph is taken away, you're still connected. Okay, so here is an example of a feasible solution. Yeah, I mean, this is something else like kind of hand drawn. So okay, so okay, suppose I give you this graph, right? These green edges are safe and those red edges are unsafe. So I claim that even if you remove one unsafe edge, it's still connected. Right? Because these can't, sorry, these can't fail, right? It's okay to, right? But these can fail, right? But I claim that even if you remove one edge, it's still connected. So this is a feasible solution. If you buy this, you're happy. Yeah. So you want, among all such feasible things, you want the cheapest one. I'm not showing the costs and the rest of it. So that's the problem. Yeah. Okay. Okay. Let me ask you. Let's connect it to something that we kind of know. Suppose I give you such an instance, and all the edges are safe. What is the problem? Yeah, every edge is green and it's MST, right? You don't have to do anything. What if all the edges are unsafe? It's two edge connectivity, right? Yeah. So okay, so it is generalizing both at the same time. I mean, it generalizes tree augmentation also for that. Yeah, yeah. So sort of like, it captures sort of like non-problems, but it's kind of somewhat funky, right? So the question is, what can we do for this problem, right? Now it turns out, as you notice, right? Okay. So in general, though, this problem, this as the connectivity increases, this notion becomes a little tricky to handle. So even though in the simple case things look okay. So okay, to get us to understand this a little bit, let me give you a definition. So suppose we have a graph which has this feature. There are some green edges, some red edges. In this graph, we'll say a pair of words is ST or PQ connected, flex connected. If SNT or PH connected, even after we remove any Q unsafe edges. Okay, so here in this case, for example, I claim in this graph SNT are 2 flex connected. That is, even if I remove any two red edges, there's still two edge connected. It's not easy to verify this one. It's so easy, right? And I also claim that 1-3 flex connected. That means even if you remove three edges, there's still one connected. Okay. So how can you verify this, right? And so you can do like the obvious sort of Manger's theorem kind of characterization. And what is the claim? The claim is that SNT or PQ flex connected, if and only if you look at any cut that separates from SNT, either you have P plus Q edges on the cut, where the color don't matter, or you have at least P edges, which are at least P safe edges. Okay. If you have at least P safe edges, that cut is safe, right? Because you want pH connectivity, and you have P safe edges, they won't fail. That cut is happy. Okay. But if you have a cut which has a lot of unsafe edges, and you still want pH connectivity after any Q of them fail, you should have P plus Q edges. So now, how can you check this? There's no easy way other than enumerating over all subsets of Q unsafe edges. So this is a weakness of this model. That how to check, you need to spend roughly M to the Q time. But we're really interested in Q being small, not very big. So we'll not worry too much about the polynomial running time aspects because we'll worry about P and Q being small. Okay, so that's the model. Okay, that's the connectivity requirement. So now we can define a network, very broad network design problem, right? Just like with the usual network design problem, everybody specifies what connectivity they want, right? I give you a graph which has safe and unsafe edges, and you say, okay, look, I want a PST, QST. This pair wants PST, QST connectivity required, right? So it's a lifting of the old problem to this more general model. Okay, it's good to define these things, and then we'll say, okay, to make sense of the general problem, we should at least understand special cases, right? The simplest two special cases of interest are single pair ST, because that's something we understand, right? Typically, SNT we want to study, and spanning we want to study, and the general case we want to study. Yeah. So this is in some sense, these two, the single pair and everybody are they kind of like easier to think about special cases. And ideally, like Jain's result, we would like to solve the big one, right? Where we get the full general. Yeah. So that these are the kind of classification we like to study. Yeah. So this is how we started. And there have been a few, I mean, we got interested in it because of some recent, even though the model was defined in 2013, but additionally there was very little progress. Till recent work in the 2020, and this Boyd et al. Paper in FSTD 21, which actually caught my eye because I was the chair of that and I was reading all these papers, right? So roughly, right, this is what we kind of knew, right? What the summary of what we knew was that the problem was only understood when one of these parameters was 1. I can't go into all the details because it's a lot of background. Or like if you wanted both P and Q, it is only possible to get some logarithmic approximation. Right? So general case is very difficult. These problems all seem quite hard, right? They didn't have much structure like the old problems which require they use submodality and very nice structure but to get Jain's result and so on. But these problems were not exhibiting good structure. So that's why we could not apply existing techniques. They were limited, right?
Certification.
Certification is a little hard, right? And so that is one of the reasons, right? There's less structure. So, but we made a bold conjecture, okay, based on the fact that we couldn't actually prove any lower bounds or integrality gaps. Our conjecture was that as long as P and Q were small, you should get a good approximation, which depend only on P and Q. Yeah. So in practice, let's say whatever practice is, right, we'll be not interested in P and Q being, even though theoretically it would be great like getting a Jain's result which doesn't care about requirement being small and large. It's a nice result, but say if you're interested in network design, most of the time P and Q are small, right? It's not a network can have it. So at least from theoretical point of view also, we thought, okay, for every P and Q which is constant, you should get a constant factor. Right? That seemed like a worthwhile goal and also couldn't find any lower bound ruling that out. Either also integrality gaps and stuff. And in fact, we couldn't even solve the single pair 2-2 or the spanning case 2-2 for this case. The first non-trivial cases for our conjecture were just these two cases. Even single pair was highly non-trivial. And couldn't figure it out. Right? Took a long time. And so let me tell you what we proved in the paper, right? And there are a lot of open problems.
How do you address the 2,1 version of the only one?
2,1. Okay, that also requires some work to prove.
Okay.
Yeah. So you have to register some capacity and network design. Nothing is trivial. Yeah, I mean, I can't give you a quick answer. Yeah. So we got, we started playing around with it, and this is what we proved. Okay. There are two sets of results we put using two different sets of techniques, completely different sets of techniques. Right? The first set of results was like, okay, we want a constant factor for small values of P and Q, right? Okay, this was quite non-trivial. Just to find a single pair 2-2, we got a 5 approximate, right? And then we had a slightly general result, okay, some fixed function of P and Q when we satisfy this inequality, P plus Q is bigger than PQ over. Why? It's not obvious, right? And so in particular, for P2 and 2Q, single pair, we can get constant factor. Okay. And then we went to the spanning case because they are the tractable case. Okay. For 2Q, we got 2Q plus 2. And for P2 and P3, we got O of P. Right. So we're playing around with this. I'll tell you a little bit about the techniques underlying this kind of results, right? So for small values of PQ and single pair and spanning, you're getting constant factor approximations, partially addressing the conjecture. Yeah. Okay. So that's one set of results. And the second set of results, second result, then we went to the big problem, full generality. Yeah. Okay. Where every pair can specify its own requirement, right? There, we were able to get a result of this form. Remember, we wanted something is dependent only on P and Q, right? We're not getting that. But some polygons sitting there, a lot of polygons, right? But at least we know the problem is not very hard. Okay? That it is, we can get approximation which depends on P, Q, and the technique is more interesting too here. Not interesting, it's different, completely different technique. Hopefully you'll see what it is a little bit. Yeah.
Can one ask, like, is it impossible to get a two approximation of something?
Okay. Now the question is, why are we if even for single pair? So the problem is actually hard. P and Q are not the same as the standard problem. It actually captures very hard. So really focus on what. Constant P and Q, we have no clue. I mean, it's APX hard for the generalized thing.
There's a login factor that makes me wonder if.
No, it may not be there. So we don't know. So the conjecture is still open that you should not depend on any log factors and stuff. Even the special cases, we don't know how to prove it. So right now, we can only prove these things. Okay. And I'll tell you what the techniques use. And then I want to mention some very nice independent work of Chekuri and others. They're related to our work, and there's also, as I mentioned, part of the interest in these problems is development of techniques. And I mean, I can't tell you what these techniques are, but there are nice primal dual ideas and stuff coming out of trying to address these problems, right? And so they can get constant factor for fixed constant for P2, we got O of P. So they're kind of incomparable when P is small, and when but they also have very nice results, right? If you're interested in this case, you look at this. Yeah. Okay. Okay. So the rest of the talk, I'll tell you a little bit about, maybe it's really a background on network design. How do we think about these problems, and what do we use, and when we get stuck, and what work, what we expect. Okay. So there is when we come up with a hard network design problem with higher connectivity, there is a very standard approach people take. It's called augmentation. So what is the augmentation approach, right? You should try to solve the entire problem in one shot. You rephrase it as like going from one, increase the connectivity slowly one by one, because the resulting problem looks a little easier. Okay, let's kind of apply that. It's called augmentation approach because you don't try to solve higher connectivity problem in one shot. You increase connectivity slowly, right? That's the name, right? So you start with the simpler problem where you say, oh, no unsafe edges can fail, right? That's P0 connectivity, right? And then, so what are you asking then? Then you're saying, I want some edge connectivity between some pair, and that you can solve using the standard problems. Then you say, okay, I need to allow like one unsafe edge to fail. Then I augment my solution to guarantee that you will solve. Then I say, okay, I need to solve maybe two edges to fail. So I try to increase Q from 0 to my requirement, right? And so this, okay, so we'll see why is that useful. Okay, so why is that useful? So let's think about it. Yeah. Okay, suppose I already satisfied connectivity requirements of Pj minus 1, right? So every pair I'm interested in requires Ph connectivity if j minus 1 red edges can fail. Now I want to go to Pj connectivity. Okay, since I already satisfied this, so what can I say? If you look at any pair that I separate that I want to connect, I already satisfied Pj minus 1 requirement, right? So that cut has at least P safe edges or P plus j minus 1 total edges. That's what the guarantee is. But I want to go up to Pj, right? But what does the cut need, right? The cut needs at least P safe edges or P plus j total edges. So the cut will be okay if it is already satisfying this, then it's also happy here, right? But when is it not happy to go up? It is currently at this level. It has only P plus j minus 1 total edges, and it needs this much, right? So those are the cuts I need to satisfy, right? In augmenting. So that's what the augmentation problem is like. We'll say a cut is deficient if it is separating some terminal pair of interest, and it doesn't have p safe edges. If it has p safe edges, I'm already happy, right? And it has less than p plus j total edges, but we know it has p plus j minus 1 safe. So it requires only one more edge to be happy. That's the advantage of the augmentation approach. This deficient cut requires only one edge to hit it. Okay. Moreover, I don't care whether it's unsafe or safe. Right? Okay. The augmentation problem corresponds to taking all these deficient cuts and adding one more edge to hit those deficient cuts. And in adding one more edge, I can forget whether they're safe or unsafe. That's good, right? Because my whole mess in this problem is because I have to distinguish the safe versus unsafe. But in this augmentation problem, we can forget what they are. We just have a traditional network design problem where we have a collection of deficient cuts and we want to hit all of them. So it's like a hitting set or set cover. But the number of such cuts is exponential, right? That's a traditional graph. The cuts will be exponential, even for ST path, the number of cuts will be exponential. But how can we solve this problem, right? Okay. So this is just this is a standard thing in network design, right? You go from higher connectivity to this 0-1 cut hitting set problem because it's a little easier. You don't have to worry about how many edges except one, right? Okay, why can't we just solve this problem? Because these deficient cuts don't have enough structure. Okay, so what does it mean? So if you go back to classical network design and Jain's algorithm or before, under what circumstance do the class of cuts have nice structure that we can solve the problem easily? Okay, and that class of cuts in the traditional, the largest scenario where we kind of know good behavior is that if this class of cuts forms what's called an uncrossable family, then this class of cuts are well behaved from our understanding so far. Yeah, roughly, I'm oversimplifying. So a very nice result in network design is that if your family of cuts is uncrossable, then hitting them is easy. Okay, that's a classical kind of result in network design. Yeah. So okay, let me define what uncrossable means, right? Then try to see. So a family of cuts is said to be uncrossable, or sometimes called skew supermodel in the more general setting. If A and B are two deficient cuts, then one of the following has to be true. A intersection B and A union B are both deficient, or A minus B and B minus A are both deficient. This is a definition of uncrossable family of cuts. Okay. So obviously there's some nice structure here, right? So what is the algorithmic advantage if the family is uncrossable? In fact, if the family is uncrossable, solving the minimum cost heating set problem for them is too approximable using primal dual or iterated problem. This is actually the backbone of many network design problems. Yeah. So this is a very large class, large and important family of cuts. So if your family satisfies that, you can use this algorithm as a black box. Yeah. Sometimes you use existing results as a black box, right? Okay. Okay. So maybe we can try to use this result, right? And it turns out that in one case it is true. Okay. If you want 2Q flex spanning, you want to go from 2K minus 1 to 2K, the resulting deficient family turns out to be uncrossable. Okay, we just observed it, it's uncrossable, so we're good, right? We can use this result as a black box. Yeah, fine. Okay, we tick that box. So okay, but then suppose you use this and you put it in an augmentation framework, you have to do it many times, you'll get 2Q plus 2 approximation, right? Because you're doing Q states. Okay, so that's the easy case. But as soon as you go to PQ, where P is bigger than 2, it turns out that this family of cuts in the augmentation framework is not uncrossable. Okay, let's look at an example just to give you a feel for it, right? And even coming up with these examples sometimes takes work, right? To understand. Okay, so let's look at this problem, right? There are 4 vertices, yeah, and there's multi-graph just to make some construction easier. So what do you want? We want to go from 3-1 to 3-2. So okay, I claimed, look at this graph. It has like the green edges which are safe. These are red edges which are unsafe. I claim they satisfy 3-1 connectivity. Okay, that means that if you look at any cut, right? In fact, there are 4 edges, right, essentially crossing any cut. So the total number of edges is 4 in all cuts, so it's safe. Now I want to go to 3-2. Yeah. So let's look at 2 deficient cut. Okay, look at A. A is a deficient cut. Why? If you look at A, how many edges are crossing here? 4, right? But only 2 are green. So if you had 3 green, it would be fine, right? But only 2 are green, so and only 4. So we want to add 1 more edge to that, yeah, to make it 3. B is also like that, right? B also has that feature that there are only 4 edges crossing, only 2 are green. Okay. Now the question is, are they uncrossable? Okay. So what is uncrossable definition? If A and B are deficient, then either A intersection B and A union B should be deficient, or not either, right? Both of them should be deficient, or A minus B and B minus A. But look at this, A union B is not deficient and B minus A is not deficient. So why is A union B not deficient? If you look at A union B, 3 green edges are there, so it's not deficient. Similarly, B minus A has 3 green edges. So neither of them is deficient, which means that this family is not uncrossed. So what do we do? Right? So we can't use it as a black box. So we have to figure out something else, right? So what did we do? We showed that we came up with
B itself has two edges.
Sorry?
B, but B has 2 clean edges.
No, but there's 4 edges crossing. No, it's okay.
Should have 3 safe. The same thing has 3 safe edges. B minus A has 3 safe edges.
Yeah, B minus A. B minus A is just this vertex, right?
But cuts means
What is
in
it?
terms of what?
Yeah. So B minus A is just this one vertex. No, but I am proving that it is cannot be uncrossable because remember, to be uncrossable, A union B and A intersection should be deficient, and or B minus A and A minus A have to be deficient. But I'm saying from each of these 2 sets, I'm showing one is not deficient, so both neither thing can be true. Right? That's what makes sense. Yeah. Okay, so what? So this forces us to think, right? What else can we do?
And also means that you can like specify like a some very polynomial subfamily.
No. You need a separation order. Uncrossable doesn't imply anything. In fact, there are uncrossable families which you cannot have you need an additional thing for hiding things.
Okay.
Uncrossable families can be exponential. In fact, most of the time the interesting things are exponential, otherwise you can use set count like arguments. Uncrossable, you need a oracle also to give you minimal violated sets and all that other stuff. Yeah. Yeah, it doesn't mean that they're polynomial size. That's not at all.
Not like min cut.
No, even min cut, the number of cuts is exponential. The minimal violated cuts are nice though.
Okay.
Yes, that's the property is true for here. Yeah.
Simple specification for the name.
Oh, because you can uncross, no? So that the name is if A and B cross, A intersection B and A union B don't cross, and A minus B and B minus A don't cross. So that is the name uncrossing.
Yeah.
If you have crossing, you can remove it. So that's why it's called uncrossing. It comes from submodularity, supermodularity kind of reasoning, and say behavior is better. There's some structure to the class of cuts you're concerned. That's all it means. Still, it's an NP-hard problem, but you can get a 2 approximation. Yeah, from this. Yeah, so that's a nice structure. So I mean, some of this is like if you work in network design, you would know, but otherwise, why would you know, right? So it is simply I'm just giving you a high-level idea of like how to think about this, and so if you are interested, you can follow. Yeah. Okay. So so then we are forced to figure out some way of tackling it, right? So the main observation that, which forces us and other groups is like, one technique that we are exploring and has some partial success is that when you're faced with this kind of a complicated problem, can you decompose your family of cards into small number of uncrossable families? And then you use an algorithm, right? And it's not at all obvious when and how you can do it, right? So you have to be lucky and you have to see in what conditions things work out, right? So what we did is like, let me give you a quick approach for P2, like the problem, right? P2, we can get something, and let's get a high level idea of what we can get, right? You try to do this augmentation, right? And then, we realize that, if you're going from 3.1 to 3.2, we don't get an uncrossable family right away, right? So we said, okay, let's look at a family of all deficient cards, yeah? Then let's further refine them, okay? Remember, we have a family of deficient cards. Let's further refine them. How do we refine them? Let's look at how many safe edges they have. Some of them have 0, some of them have 1, some of them have 2, and up to p minus 1, right? Because, right? So we'll partition this the deficient cards into p sets, okay? And then what we can prove is that, and Cj is a set of all cards that have exactly j safe edges, right? And we can prove that Cj is uncrossable if C0, C1 up to Cj minus 1 are empty. So provided that we don't have any cuts in C0 up to Cj minus 1, Cj is uncrossable. Okay, so how can you use it? What you can do is that, okay, you first cover C0 because it's uncrossable, right? And then once they cover them, they're no longer there, right? And then cover whatever is left of C1 because that family now is uncrossable. And then you go to C2 and then you cover them and so on. Okay, we're still using uncrossability, but now we can't do it in one shot, so we can't do it in this sequence. So the crux of the result is to prove this, this nicer property at least holds if we classify them like this. So we got lucky like that, okay? And then we did the same thing for P3, from P2 to P3 also this idea works. Okay, and all this, and then it fails from P3 to P4. Okay, it doesn't work, right? So what is the logic? I don't know. Okay, it worked for a few things and then stopped. Okay, so we don't know what to do at that point, right? So let's start. All right, and then single pair turned out to be even more difficult. Surprisingly, single pair turned out to be a lot more difficult. In fact, there's a big mess out there, but we can show that we can decompose this deficient cards into small number of uncrossable families where a lot of sort of technical work. I won't go into details, but I want to get this high level idea that, okay, if you have this new problem, you need things, no? And so we can't just use this uncrossability in a black box. So it's showing that at least for some special cases, there's still some structure and it's not too bad. That's what we could show. Okay, so I'll talk about this flexible connectivity in this constant factor regime because this is all we could prove, and we have some ideas, but they're somewhat still not. We didn't make any concrete progress. So I'm going to switch to the second model, and this one is like a very general model, okay? Highly general model. So let me tell you what this model is. It's called bulk robust model. Okay, so what is this model? It was introduced in 2015 by Adjiashvili, Zenklusen. So remember, we're trying to model faults, right? Okay, how do we model faults? Well, in the standard methodology, you say, okay, any k minus 1 edges can fail, right? And then we refine it with these two classes and only k minus 1 safe edges can. So in this model, we start with what's called a scenario model. Okay, what is a scenario model? I give you a long list of scenarios. In this scenario, I tell you these 3 edges can fail. On that scenario, I say those 2 edges can fail. Right? In the third scenario, I'll tell you this 5 edges concept. Yeah. So I'll just give you maybe 1,000 scenarios. Yeah. And I say, okay, even if these 3 edges fail, these pairs should be connected. In the second scenario, even if those 5 edges fail, those pairs can be connected. Yeah. So I'm explicitly telling you what edges are going to fail in each scenario. Yeah. And I'll tell you what pairs I want to connect in that scenario. It's a very different way of thinking, right? Where I can specify arbitrary correlations in this model, right? Okay, so that is the bulk numbers model. It's very, very general. Okay, now you see sort of, let's say, okay, here is a quiz going, right?
It generalizes the previous one.
Ah, okay, that's the quiz. So how can we reduce PQ flex SNDP to this model? You choose any Q minus one. No, there is a trick here. So what are the scenarios?
Like the unsafe choose minus.
Yeah.
Those are the F5. And in every KI, you list all the.
You have to do more work. Little bit more work. For each subset of at most Q unsafe edges and at most P minus one safe edges, you construct a scenario. Because this is only saying connects one connectivity. These edges fail and it still should be something should be connected. Okay. So you can, this is so general that you can express many things, including PQ flex SNDP, by brute force enumeration. Okay, fine, you can do it, but what is the advantages and disadvantages of this model? What is the price you pay for this generality? Well, how many scenarios do you have to list to encode PQ flex SNDP? You have to encode M to the P plus Q explicit scenarios. So you're listing a lot of scenarios. Right? But if P and Q are small, at least it is a polynomial. We are really trying to be very efficient here. We're just thinking about approximation. Yeah. Okay. But if you see the model is very general, arbitrary correlations are being allowed, right? Arbitrary pairs are being specified, right? So it's a very general model. So the nice thing is that it's so general that if you can do anything positive, at least you realize that something is structured. Okay, and there are some disadvantages. So maybe there's a lot of lack of structure. I'm giving you like a really general thing in what can you do. And of course, if it is too general, we can't do much. So we will use a parameter called the width of this thing, which is what is the maximum number of edges that can fail in any scenario. It makes sense that you should constrain that. No, if you allow like 1,000 edges to fail, then the problem is somewhat complicated. You're essentially dealing with 1,000 connectivity. It's just, you should suspect the problem is hard. So we'll parameterize all the results based on the K, which is the maximum number of edges that can fail. So if you go back to how we model PQ flex SNDP via this thing, K will be P plus Q, which we think of as small. K is 5 or 10. Right? Okay. So now people studied this model. They had some results for spanning and single pair. It's kind of self-positive things. So I won't mention all those details, but what can we prove, right? What we proved was that there is a randomized K to the 4 log to the 7 approximation for this bulk overstep. So it's actually tractable somehow. Even though it is very general, as long as your width is not too bad, you can get some. Okay. So as a corollary, immediately we get this result for flexes. Okay. So it's more general, but we get this result. Okay. So that's P plus Q work 4 instead of. You can get slightly better. That's you have to look inside too. I mean, I could have just said P plus Q to the 4. This is slightly better now. Corollary is like not just for fun, right? Okay. And there's a natural LP open right. Let's say an LP. Okay. Yes. Yeah, but we're proving a more general result. The original conjecture says that you don't need logs. You don't have a lower bound proving that it doesn't contact. But I suspect some log will come, but we have not been able to prove a small weight actually. Natural thing is to try set cover. But set cover, when P and Q are small, I mean K is small, it's not clear. That's one of the open problems. I mean, there are many open problems. So, if you're interested in network design or approximation, we don't understand many things.
Unweighted doesn't become simpler, or
unweighted doesn't make sense in this generality. Somehow, that's a little messy to think about. At least that's my person. Maybe there is something. Actually, no, you don't need unweighted can be reduced to weighted. Sorry, weighted can be reduced to unweighted by creating paths.
Special graph classes considered.
Yeah, sometimes, but we didn't really. So, I mean, this work is fairly new. These models are kind of new. Not as much attention as we paid. We got into it for various reasons. So, not as much as known. So, it's an early results, right? But okay. So,
Like when you say correlation earlier, I thought will model something like a distributional, like
you can try distributional things, but the thing with distributional things is that if we allow independence, we can still get a lot of edge failures happening with small probability. And those are hard to deal with.
But I guess when all is this actually captured, right? Even if it's a joint distribution.
Yes.
Sample of like polynomial scenarios. They ensure that you are sort of guarded against.
Yeah, the only reason why we have parameters being the maximum number, and when you have a probabilistic model, it's likely that you'll sample a scenario when a lot of edges fail. And then it's our results don't give meaningful. In case very large, you're not saying anything. So there's a technicality there. So, but yeah, this is what. Okay, so this is a very simple LP you can write, right? What is LP? It's easy to write. You want to find as few edges as possible, so you have variable for each edge, XE. That's easy, objective. Okay, but what is the constraint? In every scenario, you know precisely which edges are failing and what you want to. So you can get an obvious cut condition, right? You know, you say, okay, look at any pair that needs to be connected in scenario I. You know, look at all the edges that are going to fail. You remove those edges, and for every cut that separates them, you should have enough using the edges you're buying. It's very standard, easy to write because you know the scenario is explicit. Okay, so you write it down. So LP is good. Now, question is how do you round it? Right? This is like a very messy problem, very unclear, no structure, nothing in those sense. So here is where we got lucky, and I want to test this work, not ours, but so it is a very nice, powerful result from Fox 2022 by Chen Bandit. I call him. I know his first name much easier to pronounce than his last name. Liao and Zhang, and they designed this algorithm to handle some higher connectivity version of group standard. Group standard faults. So it's like a beautiful and powerful machine. Okay, and so we kind of use it. Okay, we can use it, and it's not too much work to use it. Okay, okay. So I don't have time to at all even get into the or even telling you the problems and the approach and stuff will take a lot of time, right? So, but I want to tell you what ingredients they use, right? And the two ingredients they use are Rake trees and oblivious rounding for group standard faults. These are mumbo jumbo if you don't know the background, right? Okay, but I want to tell you about these tree embeddings, which are very powerful. I mean, many of you know it, but if you don't know about them, there is this methodology in algorithms and graph theory, many applications. How do you take a graph and embed it or approximate it by some distribution of trees. Right? There are many, I mean, there are two fundamental results that are very important in algorithms. One is approximating the distances in the graphs using tree embeddings. Okay, either spanning tree embedding sometimes or just. And the other is via duality, one can prove, and they can prove several results, that you can also approximate the cut and flow structure in a graph using these tree embeddings. Okay, so these two are like very important results in algorithms. And surprisingly, it came as a kind of a surprise to me that you can use this result for this network design. And it's really remarkable. Okay? When I say it, I'm really, because I'm really impressed by the power of the method. Okay? And if you're offline, I can tell you why, because it's really very powerful. But the algorithm is extremely simple. Okay? So here is the algorithm. The algorithm, we solve the LP, and we'll think of X that we get from the LP as some capacities on the graph, right? And then we'll initialize F to be the empty set, the set of edges we've got by, and we'll repeat this algorithm for some parameter T, some polylog, whatever, right? We'll just sample some random tree from this Rice-Catley distribution that comes from using this graph as the capacities X. And then, once you sample that, you do some oblivious rounding, which is kind of like blind rounding. When I say oblivious, it doesn't pay any attention to what it's doing, right? In the sense that it's not looking at what it's trying to connect. There's a simple oblivious rounding for group standard forest using this capacities given by the Rice-Catley. And you do it, you add the edges to the thing, and you repeat it several times. It's like a set cover rounding algorithm, but using the Rice-Catley coming from the. So the algorithm is like this, right? It's like once you solve the LP, it's like very simple, no? There's nothing going on, right? You can describe the algorithm, but these two are powerful tools, right? Like a distribution. There's a little bit more going on and hiding it. Right? The overall algorithm is very simple in terms of high level. It works. Okay. Yeah. No, LP is not explored. This you can solve. This is a standard way to solve it. Is a main cut conversion. Yeah, these exponential separation of that's standard network design. Because FI explicit. No. Number of scenarios is given to you as part of the input, so it's not exponential, right? So that's why it's nice in some sense. It's kind of disadvantage in another sense. Like I'm forcing you to give me the scenarios. So my running time is allowed to depend on the number of scenarios. Okay.
Like following in PNQ are constant.
Yeah, PNQ are constant.
So number of scenarios are also following.
Oh yeah, it is fine. Like when PNQ are constant, it's fine. Not then we are in trouble. But the original problem for bulk robust, it just has scenarios given to you, right? In this case, for that, there is no notion of worrying about it. And input is the scenarios. That's why it's a disadvantage, but it is what it is. Okay, so that's all I'm going to tell you, that this algorithm works. These tools are amazing. This result is amazing. So it's quite a surprise to have this Rice-Catley stuff used in network design like this. And we can use some other techniques. I won't tell you about it. We can improve the approximation to log square n times poly k as opposed to log 7n. I won't talk about it, but you don't get an integrality gap for some reason from that idea. But anyway, I want to finish up. So what's the summary? Summary is that we have this non-uniform fault models. It's kind of new. We got interested in it for various technical reasons, and it seems that even though they're very general, you can get reasonably positive results. Right? I think of this as qualitatively that they're not terribly hard, because sometimes you come up with models, and then you can easily prove that they're very hard. Okay? And in this case, we couldn't prove that they're very hard easily for small values of P and Q, and so we sort of maybe made this conjecture and we made progress, right? And along the way, I think the problem forced us to develop, not only us, other people, connect with old and new techniques in some nice way. So it is from a theoretician's point of view useful. And there are several open problems. The conjecture is still open, right? We have these log factors. So is it necessary? But maybe there's hardness. One could try to prove hardness. And to answer Chandran's question, I guess even for this bulk robust with fixed k, we may get f of k approximation without the logs. That's not ruled out. But maybe there is a lower bound whether by an integrality gap or by a hardness that rules it out. And we don't know. So even for special cases like single source spanning, it seems difficult to prove. But it's not like we spend a lot of time. We are doing other things now. So there are many open problems, a lot of gaps between. Yeah. So that's all I have to say about this slide. Yeah.
Like the name Flex.
Flex. I don't know. It's not the name we gave. That's the name Adjiashvili gave. Yeah. So yeah, we got interested because we got stuck on some other problem, and we were like trying to see some variations.
You see, but you take FIs that are structured in some. Right now, it's an arbitrary list. Maybe